Okay, so hello everyone. Welcome to this edition of ICTS String Seminar. So today we have the pleasure of having Michal from Albert Einstein Institute in Potsdam, and he's going to tell us about space-time as a quantum circuit. So over to you, Michal.
Okay, very good. Thank you very much for the invitation. I'm very happy to give this talk. And thank you for coming to join. Today, I'll be talking about a paper that we put out together with Ramesh Chandra, Jan de Boer, Mario Flori, Sergio Hortner, and Andy Rolfe in January this year, that is titled Spacetime as a Quantum Circuit. And in my talk, what I want to do is basically present some background material that led us to this paper, as well as basically what I find as the most important content of our work. I mean, since this is a virtual seminar and I don't really see you, please feel free to interrupt me whenever you have some questions. And yeah, I'll be very happy to answer. I mean, this makes such a talk much more basically entertaining for me as well. So let me start with the broad introduction. Basically, the starting point for whatever I have to tell you is entanglement and the special role it plays in holography in ADS-CFT. And what we know, or already for about 15 years, and maybe what we know for sure for about 8 years, is that in ADS-CFT, so our best understood example of quantum gravity, entanglement entropy is nothing else. Entanglement entropy in quantum field theories, underlying microscopic description, is nothing else than the Bekenstein-Hawking entropy of certain codimension 2 surface in the gravitational picture. And this association between a quantity that, well, I should not say maybe is particularly well-defined in quantum field theory, but at least like you might have an idea of what's going on there, and a geometric quantity on the gravity side led to applications to quantum gravity. In particular, it made entanglement entropy a new and rich quantitative tool in the subject. So to put everybody on the same footing, let me start by drawing an ADS spacetime. So this is the cylinder. For definiteness, in this talk, I'll be talking mostly or perhaps even only about ADS-3 spacetimes and ADS-3 CFT2 duality. So this is the cylinder is gravitational background is the ADS-3 universe. The asymptotic boundary is basically the boundary of this. I mean, is this black region over here. It's two-dimensional, and this is where a two-dimensional quantum field theory lives. This cylinder, of course, extends in time to plus and minus infinity. We're going to be talking mostly about Euclidean situations. So this is Euclidean ADS dual to a CFT on in this case on an infinite cylinder. And if we pick a time slice in the microscopic description of a quantum field theory, that's going to be a time slice on a boundary. And on this time slice defines a state in a dual quantum field theory. So the time slice is this dashed blue region on the boundary. It defines a state. In this case, in the case of the empty anti-de Sitter space, is the vacuum state. And what we do is like we divide this spatial direction in which the CFT lives into two parts, like say an interval A and a complement A bar. And then if we calculate the reduced density matrix in A and calculate its fundamental entropy, then what Ryu and Takanagi conjectured and what Maldacena, Levkovich, and others made more concrete, this is given by the area of the, in this case, length of the codimension 2, so one-dimensional in this case, minimal surface that extends from the boundaries of the subregion on the asymptotic boundary into the bulk. So like this is basically this magenta region over here, right? So what's important is that entanglement entropy leads to many interesting insights about the nature of quantum gravity in anti-de Sitter universes, and that it's a codimension 2 surface from the point of view of dimensionality of the bulk spacetime. And one thing that one can do, and this goes under the name of, broadly speaking, kinematic space program, is that one can think of the bulk spacetime as effectively woven by such Ryuta-Kanagi surfaces. And what one does in this case is one keeps effectively the global state fixed, say the vacuum, and what one does is varying subregions. So for example, what one can do is one can take this constant time slice, and on this constant time slice, one can consider, say, all possible connected subregions, so basically all intervals that are there contained on this constant time slice on the boundary. And for each such subregion, construct the Ryuta-Kanagi surfaces, and these Ryuta-Kanagi surfaces are going to actually pass through every point on this constant time slice in the bulk as well, right? So in this sense, you can think of this particular constant time slice in the bulk as being woven by the Ryuta-Kanagi surfaces in such a way that, in principle, it's possible to recover the properties of this constant time slice from the boundary data, in this case, the entanglement entropy. So to put it in other words, one can think of at least parts of the bulk as encoded in a scalar function here, entanglement entropy, defined on a modular space of subregions in a dual conformal field theory. And as I anticipated earlier, in two boundary dimensions, such subregions are defined by pairs of points. And then it turns out that a very nice organizing principle for these sort of considerations goes under, broadly speaking, the name of kinematic space or moduli space of causal diamond. And it turns out that the natural geometry that you can associate with pairs of points is going to be a two-dimensional Lorentzian de Sitter geometry. And this is a geometry in which Ryuta-Kanagi surfaces really are points. It's an auxiliary geometry that is very useful, actually, and is going to appear later in the talk in understanding or basically in operating with entanglement entropy in two-dimensional conformal field theories in holography and outside.
Michal, can I interrupt you?
Sure.
So what is moduli space in this case?
So in this case, what you look at is you look at a conformal group that preserves the subgroup of a conformal group that preserves a given time slice. So in this case, it's SO1, 2. Mm-hmm. And then there's going to be a stabilizer group that's going to be preserving a given configuration. So in this case, like a given pair of points. Mm-hmm. And the geometry that you talk about is a quotient geometry, and this quotient in particular is a two-dimensional de Sitter geometry. So that's roughly speaking the idea, and I mean, maybe I can come back to this a bit later when it becomes relevant. Here, I just want to advertise it.
Okay.
Yeah. So for the higher dimensions, do the moduli space reduces to some de Sitter?
Oh, that's a very good question. So if you look at so there are two things that you can do. So one thing that you can do is you can consider. So what? Let me go back. So like in higher dimensions, things are a bit more complicated because if you think about subregions, even on a constant time slice, these subregions are connected. Subregions are not really pairs of points, but are basically arbitrary curves in two dimensions, right? If you think about 2 + 1 dimensional quantum field theories, you pick a time slice, so you're in a two-dimensional, say, flat space. And then if you want to pick a subregion there, I mean, it's going to be some complicated, curve that specifies a subregion. It's specified by infinitely many parameters. But there's a special case of curves, which are circles in 2 + 1 dimension, and high dimensions are spheres, and with a special property that conformal transformations map a sphere into a sphere. So if you restrict yourself to such subregions, it turns out that you can construct a similar quotient, and it's going to be a higher dimensional de Sitter space. So for D + 1 dimensional conformal field theories, it's going to be D + 1 dimensional de Sitter space. But this is only the case if you think about subregions that are defined on a constant time slice. You can play the same game, but relax the restriction that you focus on a constant time slice. And in this case, actually, you don't get de Sitter anymore. you get a more complicated space that's going to have d space and d plus 1 space and d plus 1 time directions. And de Sitter arises there as some particular submanifold, I think. And this is the topic of basically this paper and that paper. But I will not be concerned with these more complicated examples. Did this answer your question?
Yes, thank you.
Sure. Okay, so entanglement entropy clearly is important for ADS CFT. And in certain cases like MTEDS, entanglement entropy allows you, through these sort of kinematic space considerations, to reconstruct the geometry of a constant time slice. And then by varying time slices, you can think of reconstructing the full geometry of Untitled Chapter space. It's a bit similar to the ideas that led to derivation of linearized and then also nonlinear Einstein's equations in the case of using the ideas from modular Hamiltonians, etc. However, what is also known and also well appreciated now is that entanglement is not enough, in a sense that there are situations, for example, in spacetimes involving black holes, where there are entanglement shadows, which are there are regions that are not penetrated by any codimension 2 surface that is associated with entanglement entropy. That led to a parallel line of development that's going to be the main topic of this talk, which is not to restrict oneself to codimension 2 observables in quantum gravitational theories, but actually also look at codimension 1 and codimension 0 covariant gravitational observables. So just to sketch what such observables are, well, this is the same picture that that I had before, right? Like we have here constant time slice on the boundary, and now if one were to identify a covariant gravitational observable associated with this full constant time slice, so like the full state in a dual quantum field theory, what you would do is you would consider, for example, a codimension 1 surface that is spanned by this boundary time slice. And then, of course, there's going to be infinitely many such surfaces that you can consider. But similarly to entanglement entropy, what you want is you want to put some extremization constraint. And what you're going to be picking is a minimal codimension 1 volume slice in the Euclidean case, or in the Lorentzian correspondingly, a maximal volume time slice. So such objects are uniquely defined. And what is known about them is, in particular, that they probe beyond entanglement shadows. So they are complementary quantities with respect to holographic entanglement entropy, defined in a standard way. And well, one question that you can have already straight on is that since they are well-defined gravitational observables, what is their quantum field theory description? What is their interpretation in terms of quantum field theory? And this is something that basically dates back to the works by researchers at Stanford around Lenny Susskind, and then that was taken over by many groups around the world. And the conjecture interpretation of these objects, so these maximal or minimal volume time slices, is based on the conjecture gravity interpretation of tensor networks. And the idea basically is that such surfaces quantify complexity understood as hardness of state preparation using limited resources. So this might sound quite exotic, but the logic basically was that if one follows basically Brian Swingle's idea that constant time slice in ADS represents a Mera tensor network, this Mera tensor network, I mean, let's not dwell into details, it's not really relevant for us here, can be depicted by this graph that you see here on this constant time slice. This Mera tensor network is basically constructed as a contraction of some tensors. And basically, if you calculate the volume of the space within this identification that Brian pursued, the volume of the constant time slice would be related to the number of tensors in the network. And since the more tensors you have, the more complicated it is to prepare a state, this is the origin of the association of these volumes with the notion of complexity. This is basically the heuristics behind these objects, and of course, an obvious question is, can one do better? So can one be much more microscopic regarding these codimension 1 objects? And this is the subject basically of the rest of my talk. So what I want to describe are various attempts that I did with my collaborators in the course of the past, say, 4 years in trying to understand what these guys really are in underlying quantum field theories. Are there any questions about this? Good. So let me keep going. So you should not be worried if this notion of complexity sounds a bit exotic, although I'm pretty sure that you heard about it in many talks already. One thing that you can ask yourself is, can one come up with a simple example that illustrates it? And can one make this example quantitative in such a way that it generalizes to quantum field theories in general, and in particular to holographic quantum field theories? And this is basically the subject of the rest of the talk. So in order to put everybody on the common ground, I want to discuss a very simple example in which the notion of complexity is going to become more obvious, hopefully. And this example is going to generalize straightforwardly to more complicated quantum mechanical systems, which doesn't mean that it's going to be easy to operate with. So let's imagine the following situation, that somebody gives you like a single spin, so like 1 qubit in quantum information parlor, and one provides you with a task. So what you're given is a spin pointing along the x-axis, so like this this reddish object over here. So it's in the eigenstate pointing along the x-axis, and the task that you're supposed to do, using limited resources or using some resources, is to provide the spin or transform it to point along the z direction, so like this bluish state over here. And the resources that you're provided with are rotations. So you're allowed to act with exponences of Pauli matrices, let's say for definiteness of all of them, all 3 of them. And if you ask say an undergrad student to do this, probably like the answer that you would get is that you're supposed to rotate the spin along the y-axis by an angle, say pi half, and this is going to do the job for you. And in this, indeed, like probably like that's the simplest thing that would occur to everyone. But truth to be said, of course, there are infinitely many unitary transformations that do this job for us. For example, one can first rotate along the z-axis, so that the spin from pointing along the x direction starts pointing along the y direction, and then one can rotate along the x-axis in such a way that the spin pointing from the y direction starts pointing in the z direction, and we claim success. And probably this is not the situation that you would this is not the scenario that you would come up as the most natural one. And at least if I ask myself, why is it so? Then naively, at least, like the conclusion that I would reach is that over here we had to rotate like by an angle of pi half. And in this case, we would have to rotate by 2 times angle pi half using 2 different Pauli matrices. And clearly pi half is smaller than 2 times pi half. And this is the intuition that at least myself, I would call this transformation simpler than this one. But that might not be entirely appropriate. And the reason for it is that nobody really told us that rotations along all directions are, equally cheap or equally costly. In a sense, for some practical reasons, it might be that rotation along the y direction is 10 times harder to do than rotations along the remaining axis. And if this is the case, in fact, the first scenario, according to this logic, would be 5 times more hard than the second scenario, and the second scenario would win in this competition between the two. So what I'm trying to convey with my words is that when it comes to defining a hardness of transforming one state into the other, it's not something that is given once and for all. It really depends of what we quantify as cheap and what we quantify as expensive. But regardless of these choices, what's important is that when we do the transformation using unitary gates that are exponences of some generators, then a very natural thing to do would be to quantify cost of the transformation by looking at basically like the total distance that you travel in the space of your generator. So basically how many times you had to apply each individual generator. That's going to depend of what's basically the prefactor, what's the sum of prefactors in front of all generators, right? And now once one does it, there is still a choice in discounting, which basically tells us how to discount one generator with respect to the other, right? And well, this is all these words are kind of obvious, and I've been giving this example to various audiences just to build an intuition about complexity. But it turns out that this example actually is very nice and rich. And about 2 years ago, Adam Brown and Lenny Saskind wrote a paper devoted entirely to this example. So if you want to learn more about it, please have a look. It's a very nice paper. But the key thing for us is that this approach that originates from works by Michael Nielsen and collaborator is an approach that actually naturally generalizes to quantum field theories. And this was something that was realized by myself and collaborators, and in parallel by Rob Myers and Rob Jefferson in 2017. So if one were to abstract away from the picture of a single spin, I mean, one would say that there is some reference state and there is a target state that one is interested in. And the transformation between these two is given by, say, for now, a unitary transformation. This unitary transformation is basically an evolution in some auxiliary time, say, that I'm going to denote here by tau, with some time-dependent auxiliary Hamiltonian that does not really have to have anything to do with the underlying Hamiltonian. And this auxiliary Hamiltonian is decomposed into the generators. So like these are our elementary Hermitian operators, in this case, like the Pauli matrices. And then each of these generators is going to be applied at a given step of transformation by this epsilon I d tau number of times. And then if one were to assign a cost to such a transformation, what one would have to do is one would have to integrate over all circuits, so from 0 to 1 in the circuit parameter. The cost of each individual invocation of an operator is epsilon I d tau. We have to sum over all operators involved, and different operators are discounted in principle in different ways. And in this way, by assigning these weights by I, we account for this. So basically what we have to do is we have to minimize, in other words, an L1 norm in an auxiliary space that is defined by the transformations that we consider. And now, taking from there, you might start wondering, okay, I mean, like, maybe L1 norm is the most natural thing from counting the number of operators is here, but perhaps you can use an L2 norm and perhaps other norms as well. And it turns out that this is a very natural language to consider in which minimizing the cost of obtaining one state from the other reduces to a geometric problem of finding minimal paths in some auxiliary geometry. And what's really interesting is that implementation of these ideas in free conformal field theory is capable of reproducing static properties of these quantities in ADS spacetime, which provided a strong momentum for further investigations of how this kind of a framework applies to quantum field theories. Any questions about this? Okay.
May I ask you something?
Of course.
The fact that it's a conformal theory and the ADS space, is this enforced to us by the symmetries of the problem, or there is a dynamical content in here? You mentioned that it's a free CFT in this case.
Oh, okay, very good. No, that's an excellent question. So, so what we wanted to do is we wanted this picture clearly of codimension one observables in gravitational theories does not really rely on conformal symmetry. I mean, like, the only thing that you want to have is you want to have a notion of asymptotic boundary, right? And you define a time slice there to define a state. This can be a holographic conformal or non-conformal quantum field theory, you choose. And then what you're supposed to do there is to find the minimal or maximal volume surface, right? And that you can always do. Now here, what we wanted to do is we wanted to give it a try in the simplest setting possible. And as you can imagine, the bottleneck here is to do optimization, so this minimization over different possible ways of obtaining a state of interest, right? So in this case, a vacuum in a quantum field theory. So the idea is that the idea that we had is that it's going to be the simplest in a setting in which we can use Gaussian techniques to represent both the state we're starting with and the state we end up with. And this basically forced upon us considering free conformal field theories. And that was the reason why we chose it. Now, you might say these are free quantum field theories. Holography works for very strongly coupled quantum field theories. So isn't there some tension? And my response to this would be that even if you look at entanglement entropy, some features of entanglement entropy are shared between strongly and weakly coupled quantum field theories. One example of such a quantity in the case of entanglement entropy are things that are protected by conformal symmetry. But the other example, which is more similar to this case, is the divergence with the cutoff, right? Entanglement entropy, holographic entanglement entropy is a quantity that extends all the way to the boundary. So the length of this, or the area of this minimal surface is divergent. And you can ask the question, how does it diverge with the cutoff in ADS? And it turns out that it diverges in the same way as the calculations of entanglement entropy in say free quantum field theories suggest it diverges, right? And basically what I'm saying here is that we encountered the same structure of divergences for free quantum field theories as for these holographic complexity proposals. Like, that's the idea.
Thank you. Thank you.
Sure. So let me move on. So the punchline from here is that well, there's a working way of defining this notion of hardness of state preparation in quantum field theory, and you can ask a question like, are there other ways to achieve the same goal? And the answer is that yeah, I mean, like, there are other things that you can try to do. And one thing that I want to emphasize is that when you ask people doing numerical quantum field theory, so lattice quantum field theory, or people doing quantum many-body systems about state preparation, they would rarely come up with a state preparation that involves unitary transformations. Instead, what they would do is they would, assuming that they consider a gapped Hamiltonian, they would perform a Euclidean time evolution for long enough, starting with some appropriately chosen state. And this Euclidean time evolution for long enough time for a system with a gap is going to act as a projector to the ground state. So what I'm trying to say is that there is an incentive in trying to think about cost assigned not to unitary transformations, but to transformations that involve Euclidean time evolution. So these are transformations that involve not only unitary, not necessarily unitary, but also Hermitian sort of element. And this is basically the story of the path integral optimization due to the Kyoto group that actually precedes these efforts that I discussed a moment ago. And let me present this in a very simple setting that originates from my work with the group here in Potsdam. So in conformal field theories, in 2 dimensions, 1 plus 1 dimension, Weyl rescalings act as redundancies in the following sense. So let's think that you're interested in preparing a thermal density matrix, and you can think about this thermal density matrix either as Euclidean time evolution or just as a thermal density matrix, right? As a state. It's up to you. And if you were to prepare it using path integral formalism, what you would do is you would consider the path integral for your conformal field theory on a slab of flat Euclidean space, right, with this metric, right? And the slab of Euclidean space would extend in X, either X being unbounded or maybe like being circular. And what's more important is that in time it extends from time say equals 0 to times equal beta, right? And this is related to the fact that we want to have like a beta sitting here. So the idea is that if we put boundary conditions on our fundamental fields here and there, what we effectively and do the path integral, what for quantum field theory, in this case conformal field theory, what we obtain matrix elements of perhaps unnormalized e to the minus beta h in the states defined by the boundary conditions. But now in conformal field theory, something very special happens. So imagine that we do a Weyl rescaling of this geometry. So we no longer talk about as a slab of a flat geometry, but we allow there to be a Weyl factor in front. And what's crucial, we want this Weyl factor to vanish at the initial and final surface, so where we define our matrix elements. And the beauty of conformal field theory is that the action does not change under Weyl rescalings, but we get a contribution from the measure. But the contribution from the measure does not really depend on what we pick here as the matrix elements. So what I'm saying is that as long as this Weyl factor vanish here at the boundaries, the omega vanish here at the boundaries, so the Weyl factor goes to 1. We obtain still the matrix elements of the same operator, perhaps with a different normalization, right? So the ability to include the changes in the geometry here are basically redundancies in determining e to the minus beta h, understood either as time evolution operator or as a density matrix, okay? And you might wonder, is there a natural way to associate a cost to these redundancies? Maybe without even thinking what this cost really entails. And the idea pursued by the Kyoto group from 2017 in many papers that actually is a very nice idea, considered a very nice idea, is to assign a cost to be the Liouville action evaluated in the geometry defined by a given Weyl factor. And this Liouville action consists of 2 pieces. There is a potential term, e to the 2 omega, that is sort of like a cosmological constant term in geometric terms. And there's also a kinetic term that is sensitive to how omega changes in t and in x. So that was the proposal. And what you can do is you can define the best way of preparing a thermal state or time evolution by minimizing the Liouville action with the boundary conditions that you want. So this is the path integral optimization proposal. And when thinking about it with my group, we realized actually that this path integral optimization is nothing else than basically this framework that I described here. But now, instead of thinking about just unitary transformations, you allow for this path integral to be defined in terms of Hermitian gates that correspond to Euclidean time evolution, and unitary gates that correspond to basically dilating your system. And these are unitary because they basically well, they are basically just scale transformations in your theory that are generated by in a unitary way. And then it turns out that there is a way of assigning weights to these things in such a way that the result approximates the legal action. And as a result, you perhaps should think of this path integral optimization procedure as a part of this gate counting that I described so far, but just allowing gates that are non-unitary, that are Hermitian. So before I ask again for questions, let me come to the key point of the talk, which is spacetime as a quantum circuit. So I was trying to be consistently Euclidean, but now let's be completely Euclidean, and let's look at ADS3, Euclidean ADS3. And what one can do is one can take Euclidean ADS3 and one can cut it into two halves along some constant time slice on the boundary, starting from a boundary. And now what one can think is that the Euclidean time evolution that is encoded by half of this Euclidean ADS3 spacetime is nothing else than a preparation of an unnormalized vacuum state using Euclidean time evolution on the asymptotic boundary. And so basically the fact that we have asymptotic boundary here means that what we're doing is we are progressing in time, and at each time step, we are basically including one layer of Euclidean time evolution of a Hamiltonian, that is your CFT Hamiltonian. And then perhaps here in the far past, we started with some state that, well, we lost track of because we've been doing this procedure for a very long Euclidean time. And now, Tadashi Takayanagi in 2018 came up with a very nice idea that was very heuristic at the same time, that perhaps, this is our asymptotic boundary, and here we know what's going on. But what we can try to do is we can try to move this boundary onward in such a way that now this notion of a boundary does not extend all the way to infinity. It resides at some finite distance from, say, the center or at any point in the bulk. But still, this defines for us some circuit, and because these new boundaries extend to the same constant time slice on the asymptotic boundary, such a circuit still defines a state. Such a circuit acting on something here still defines a state in the Hilbert space of your original holographic CFT. So it's an alternative state preparation of the ground state in a holographic CFT. And what you can do is you can imagine that these, you bend these boundaries inwards, first you consider this asymptotic, then you consider this, and then maybe you consider this, and you bend it inwards in a way that the circuit suddenly starts living on a minimal volume slice in this case. And from this logic, it would be then very natural to think about, the volume of this time slice as, related to the circuit complexity, right? Like for all these boundaries, like you evaluate some cost function, maybe volume, maybe something else. And for different ones, it's going to be different. And then maybe for this one, it's minimal. And since every single one of them defines a circuit that prepares for you the same state, then indeed, you should think about codimension 1 objects in the bulk as state preparation, and some of these objects are going to be optimal with respect to some notion of optimality. So I'm saying this in conjunction with this path integral optimization program. The reason being that it is known from the outset that path integral optimization produces a hyperbolic geometry, so a geometry of, in particular, this minimal volume time slice, as an optimum of the Liouville action in the limit when this beta goes to infinity. So this was basically the original motivation for the proposal, that it's a it's a nice way to get this new covariant gravitational observable. So while superficially this may well be the case, and one can call it a day and move on, it turns out, if you think about it for a bit, that some additional caution is required. And there are at least 3 reasons for it that I want to describe in the following. So first, in a ADS3 geometry, within an ADS3 geometry, there are in fact infinitely many hyperbolic disks that are embedded. In particular, you can foliate the whole geometry in terms of a 1-parameter family of hyperbolic disks. And from this perspective, it's not really clear if a hyperbolic disk is an optimum of this one, which one it is. So one would have to do some further studies in order to realize this. The other thing that is really puzzling is that the Liouville action should not be really seen as something that exists just by itself. There are 2 terms here, and these terms actually, just looking at their omega dependence, they have different dimensionality, right? This is a kinetic term, so it has a derivative, and this is the potential term that is dimensionless. And in order to add these 2 together, you have to provide a dimensionful scale. And in conformal field theory, there are no scales. So the only way that such a scale should arise is via the UV cutoff. And of course, when you allow for the UV cutoff, then there's going to be also terms that come with positive powers of UV cutoff that you just neglected at this level. And now, when you optimize this Liouville action, so when you just evaluate classical equations of motion for omega, then it's not, it should not come as a surprise that this induces or forces upon us variation of omega over the scale associated with the UV cutoff. So if there are some other terms that exist here, then these terms in the regime that we end up with are going to affect the omega that we get. So what I'm trying to say is that optimization of this, in principle, violates the assumption underlying the gradient expansion for this, so to speak, effective action. So I'm not saying that these things are like lethal things for the pattern-driven optimization program. Actually, quite the contrary. It just motivates us to see how to embed it in some larger framework that would allow us to get what we want, which is to define in terms of underlying quantum field theory the volume of minimal volume codimension 1 time slice. So let me say also this and take some questions before I come to the point of my talk. So one thing that should be said is that well, I mean, we might think about bending the boundary inwards, but one should be really careful about it because when we do this, we actually lose the connection, or we lose the straightforward connection to the machinery of conformal field theory. The reason being that this, now we know due to the work by McGough, Mazzei, and Ferlinda, building on early work by Zamolchikov and others in the context of quantum field theory, that moving inwards in ADS corresponds to following an RG flow that is triggered by the irrelevant deformation that is a square of the stress tensor. So when we pick this constant time size where we define a state in our original CFT, however, we consider circuits that are defined by boundaries that are not asymptotic, actually, we necessarily consider circuits that are not circuits doing Euclidean time evolution with the Hamiltonian of your underlying CFT, but these are circuits that utilize the Hamiltonian of TT bar deformed boundary CFT, and they also utilize TT bar deformations in order to proceed from one time slice to the other, because in these 2 cases the cutoffs changes. So what I'm trying to say is that this idea that originates from Kyoto, in which one thinks about different codimension 1 surfaces in the bulk as defining circuits is a very nice idea that should survive. However, what one should do is one should supplement this idea with ingredients that go beyond the CFT and involve the notion of the TT bar deformation. So this is basically all that I had to say, building the stage for the actual effort that we did in our work. So it's a very good time to take questions and then proceed to finalize the talk. So if you have any questions, please ask.
Hello.
Yes. Hi.
Hi, Michal. I just wanted to ask a question which is slightly related. So, like, is there any chance that any such proposal could be, say, derived, so to speak, let's say in some matrix model or something else? I mean, some other, yeah, which would give us, like a precise notion of whether such a thing is true and in what sense it is true. Has there been any, example of that kind, any understanding of that kind?
So thanks for the question. So apart from attempts that were, so I would say that like to date, most of the attempts in trying to understand these codimension 1 surfaces followed either lines of doing free quantum field theory calculations and trying to count on universalities similar to universalities emerging in the case of entanglement entropy and other observables, for example, thermodynamic observables, and these holographic complexity proposals, right? So, I mean, as I described, like looking at the structure of leading UV divergences, or looking at thermal states, so thermal field double states, and doing the analysis in thermal field double states in free quantum field theories and comparing the two. So this was like one line of research. The other line of research was to consider conformal field theories and try to look at quantities that originate entirely from the Virasoro algebra, and trying to seek for manifestation of these on both sides of ADS-CFT correspondence. So I would say that these are like the two mainstream goals. And I think like the thing that falls closest to what you had in mind arose in the context of the SYK model. So there are papers written by Vijay Balasubramanian and collaborators at UPenn, which look at complexity for in a realization of SYK, and trying to compare it with what one expects to get in ADS2 or like in JT gravity. And I feel like that's probably the closest to what you wanted.
Okay, thanks.
Sure. Anything else? Okay, if there are no other questions, let me move on, and let me describe our proposal, which resolves some of the issues that I pointed out and also motivates, of course, further research. So now it's going to get a bit more technical, but not too much more technical. So for definiteness, we're going to consider a Poincare patch of Euclidean ADS, which is given by this metric. And what we're going to be looking at are circuits that interpolate between vacua of theories defined by two cutoffs. So this is the Euclidean time direction in ADS3, Euclidean ADS3. This is the Z direction, so the radial direction ADS. And you might think that perpendicular to your screen, there runs a spatial direction on the boundary, but that's not going to be really relevant because we're not going to be looking at quantities that vary with position. So you might effectively forget about it. So the circuits that we would have in mind would start at some initial time and end at some final time. And these times are at the same, it's a circuit parameter, but simultaneously, it's also a physical time that exists in your system in which the time evolution is governed by the physical Hamiltonian. Now, the thing is that the starting point and the end point are going to be the states that are defined by two different cutoffs in ADS. So like there's going to be initial cutoff and final cutoff. So if you take both Zi and Zf to approach 0, so like to approach this axis, then the starting point and the end point basically correspond to states in your underlying CFT, the vacuum state in your underlying CFT. If you allow them to take non-zero values, then they correspond to vacuum states in TT bar deformed CFT. And now we're going to be interpolating between these two states via circuits that are just defined as a wiggly boundary. And such a wiggly boundary is defined by Z as a function of t. And we're going to be denoting this function by rho of t. And what such circuits do is they necessarily do two things. So there's a time evolution, right? Because we want to get in principle, there's a time evolution. In general, there's a time evolution because we want to go from the initial to final time. But there's also some coarse graining on the way because these states are associated with two different cutoffs. And this is the setup. This is supposed to be, I believe this is probably like the simplest setup that one can do. And now our proposal is to assign a cost to this setup being nothing else than a gravitational action evaluated in the shaded region M that is defined by these two maximum volume slices, say, and this not necessarily asymptotic boundary that is defined by this function rho of t. So such an action is defined in terms of the standard Einstein-Hilbert term, cosmological constant, with a choice that we make for the curvature scale of ADS. There's also a Gibbons-Hawking term on all the boundaries of this region, and then there's one more term which is nothing else than a joint term. But what we want to do is for reasons that are going to be apparent in a sec, we don't want to add to this action a volume counter term that you would normally do if you were to evaluate, for example, partition functions in ADS CFT that render partition functions finite. So this is our proposal, and we just want to take it for granted, and we just want to see how far we can go with it. And if you do this, then it turns out that the action that you obtain from this consideration is given by this functional of this rho of t. And when you integrate it by parts, you end up with this simple functional that is basically 1 over rho squared, and there's like a rho dot arctangent rho dot over rho squared, plus a contribution that comes from the corner terms that are defined here and there, which is this. And when one stares at it, actually, so when one takes this part and one expands it in the vicinity of the UV boundary, so one allows this rho of t to float here in the asymptotic region in the vicinity of 0, then it turns out that what one gets is the Liouville action plus corrections. So one would say that this proposal very naturally includes the path integral optimization as a special case, because the path integral optimization was based on optimizing the alluvial action, so this piece with respect to omega, what we're going to do, we're going to be optimizing this guy with respect to rho of t. And in the limit where rho becomes very close to 0, this is the same as optimizing the alluvial action. However, it includes all order resummation in the units of the UV cutoff. So in this sense, it's capable of resolving some of the confusions that we had regarding the original patent optimization proposal. So what we want to do is we want to...
Sorry, could you say what IC was again?
Oh, very good. Yeah, so thanks for the question. So the boundary of the gravitational region that we consider has corners, right? Because here's a minimal volume time slice, here's a minimal volume time slice, and these minimal volume time slice meet this cutoff boundary rho of t here and there, right? And when you have a gravitational action in such a region with corners, in order for the variational principle to be well defined, you need to add terms that live at these corners, right? And these are standard terms that were born in the studies of gravitational action a long time ago. And basically, what they depend on is a proper length of the segment that encapsulate the corner times the angle between the normal vectors at the surfaces that meet at the corner. And then there is some prefactor that I don't remember at the moment, but this is basically it. Does that answer your question?
Yeah, so should I interpret them as some brain contributions or something, or because these are terms in the bulk, right?
Well, I would not. Well, okay. I'm not sure, but maybe I would not push it that far. The reason being that, well, I mean, like when I would be talking about the brain, so recently there was a revival of interest in these models of boundary CFT, right? And there, when one defines the gravity dual to a boundary CFT, one does have a brain there, right? And this brain comes with some tension. But this is a codimensional 1 object. I mean, these guys over here are codimension 2 objects. And well, I mean, if you want to call them a brain, maybe you want to call them a brain. But the thing is that the tension term in this brain is very weird, right? Because it depends on an angle between 2 null normals, right? So maybe I would not push this interpretation myself.
Okay, thank you.
Thanks. Yeah, so maybe one thing that I want to emphasize is that we don't want to do anything exotic. We don't want to introduce any brains or anything like this. We just want to take the gravitational action that you would have that has a well-defined variational principle, and then minimize it with respect to the parameters in the problem, right? And that's it. I mean, we don't want to include any additional ingredients because we want to have something that is as canonical as possible. So to this end, our proposal is a 2-stage optimization procedure. So what we want to fix is the initial cutoff and the final cutoff, right? Because these define for us a state. And then in the first stage of optimization, what we're going to do is we're going to fix the time difference between initial time, between the final time and initial time, right? So we fix this delta t, and for a fixed delta t, and fix initial cutoff and final cutoff, we minimize the action with respect to rho of t. So what we're going to do, we're going to evaluate the all the Lagrange equations for rho of t. We get a second order differential equation. This differential equation has a well-posed solution that is given by this answer. It's very simple. And now what we do is we plug this solution back to the action, and as a result, this is the on-shell action that we get. But this action is not entirely on-shell because nobody really told us what the time duration should be. So what we can also do, or like what we should also do in the second step of evaluation, was to vary with respect to the time difference, right? So everything depends on the time difference, right? Because the setup is time translationally invariant, right? So when we vary actually with respect to time difference, it turns out that the answer is the smallest when the time difference goes to 0. And as a result, like what happens, the optimal circuit according to this action cost is a circuit that degenerates and is defined on a constant time slice. So this is a circuit that does not involve any time evolution per se. It just involves coarse graining. And when you evaluate the action on shell, this gives you basically the volume, the volume of the time slice multiplied by a constant that originates from the prefactor of the action, so 1/16 pi d Newton. And one of the weaknesses of the volume proposal, the original volume proposal, is that the normalization of the action, normalization of the volume was a bit arbitrary. And here, because we start with the action as our starting point of considerations, the normalization of the volume that we get as a representation of the optimal circuit is fixed in terms of the central charge, or like it's fixed in terms of the Planck length, so to speak. So this is like one nice benefit. And of course, if you take the initial cutoff to infinity and the final cutoff to the asymptotic boundary, what you basically get is the result of the holographic volume complexity proposal. So in a sense, you might think of it as a derivation of the volume proposal, taking as an additional ingredient the action as a defining cost function for the circuit. So, so you might wonder if it's really natural to consider the action as a cost function, and this is something that that is a bit complicated. So if you think about the circuits more carefully, then like when you go say by an infinitesimal step in time, and this rho of t actually exhibits some dependence on time, that means that two things happen simultaneously. So one thing is that you apply Euclidean time evolution with a Hamiltonian associated with a given cutoff theory. But the other thing is that you also coarse grain, and this coarse graining is encapsulated by insertion of the TT bar operator, right? And when you write it, you act, of course, with the circuit on the state in the theory of the initial cutoff. And now when you stare at it, a straightforward counting algorithm that you can come up with would be, like to say, okay, the more I evolve in Euclidean time, the more costly it's gonna become, and the more I coarse grain, the more costly it's gonna become, right? So to this end, I just assign a cost to the prefactor in terms of time evolution and the prefactor in terms of coarse graining. And if I do this, then the natural cost function would be the integral of, here the prefactor is 1, so like there is 1, and here the prefactor is absolute value of rho of t dt. So now I'm supposed to minimize it over all delta t and over all rho of t. And it turns out that when you do this, the answer is zf minus zi. And of course, the coefficient here is arbitrary. And this is a different answer than what you get for the complexity equals to volume proposal, and what you get from the action. So what I'm saying is that there's a way of introducing gate counting, as I did in the case of single spin or single qubit and rotations by Pauli matrices. But actually, it's quite tricky to explain the action as a cost function using this approach. And the chief reason for it is that in the action there is this term rho dot arcus tangent rho dot. And this term is the one that gives us really trouble, because it uses some very non-trivial dependence on rho dot that we don't really understand. And before I conclude, there is actually a way to reproduce the action as a counting, and this takes us back to this kinematic space approach. And perhaps it's actually quite special to the family of circuits that we consider. So So one question that you might have is how to define these circuits that we have in terms of some data in the underlying conformal field theory. So not necessarily in the TT-bar deform theory, but in an underlying conformal field theory. And you see, like the circuit is entirely defined in terms of this function rho of t. And this function of rho of t can be defined either by like providing rho of t at a given time. And the rho of t at a given time can be provided by looking at a Ryuta-Kanagi surface that lives at a given value of time, right? And it touches this boundary that defines for us the circuit, right? Like this non-asymptotic boundary that defines for us the circuit. And such a Ryuta-Kanagi surfaces in ADS 3 are nothing else than just semicircles. So such a Ryuta-Kanagi surface would, on the boundary, say, reach extent between axes of plus minus rho of t. And the other possibility that I'm going to call exotic Ryuta-Kanagi is to look at this at a codimension 2, so here a circle, that is tangent to this surface defining a circuit, but extends not in spatial direction, but in time direction, right? And it turns out that when you choose this option, such a surface is specified by the extending time, so like t1 and t2, and this extending time is given by a more complicated function of rho, involving also derivatives of rho. And as I said, in connection with kinematic space, space of such circles comes naturally with a de Sitter metric. So such a de Sitter metric is going to depend on the endpoints of such circles. So like in the case of the standard RT, this is the metric. In the case of this exotic RT, this is the metric. And now if one considers a cost that is given by the basically length that you traverse in these auxiliary spaces, that in the case of the standard RT, you don't get something that is particularly insightful. In fact, what you get is very similar to these sort of countings that I was advocating in. But if you take like this exotic one, actually, what you get is something that looks like the integral of the absolute value of the action density. So it's actually very close to what we wanted to get. So this is the sense in which the cost function that we define can be perhaps understood using the kinematic space picture, although this wouldn't be really a kinematic space for standard Ryuta-Kanagi surfaces, but this would be more like an exotic Ryuta-Kanagi surfaces that are involved. Exotic because they extend in time. Although this is a Euclidean construction, so perhaps like the distinction between time and space direction is not sharp anymore. So before I take questions, let me summarize what I said so far, and sorry for running a few minutes late. So in the paper that appeared in January with Ramesh, Jan, Mario, Sergio, and Andy, we took as a point of departure the perspective that when holographic entanglement entropy was born in 2006, one could refer to universal results and universal tools in two-dimensional conformal field theory to corroborate it and eventually to derive it. And unfortunately, 8 years after the introduction of holographic complexity, at a quantitative level, we are not much closer, we are not much farther with respect to where we started than what for entanglement entropy has been the area law, which is like the agreement between the leading divergence and in across different quantum field theory. And I would say that one of the, or maybe even the most promising idea in trying to understand holographic complexity is an idea that codimension 1 volumes in bulk define circuits. And if one takes it as a point of departure, then minimal or extremal codimension 1 volumes are then just particular examples of circuits, and then understanding of these gravitational observables amounts to understanding what is really special about the circuits that one considers in this case. So this is a big idea, and in our work in this paper we made it a bit more precise by making it explicit that the circuits that one is after in this case are not the circuits that are directly defined in the underlying CFT, but rather involve this TT bar deformations of CFTs. We propose actually the bulk action as a cost function that reproduces CV, at least in the case of empty anti-de Sitter space. And apart from looking at the gate counting and understanding the hardness or like the difficulty of obtaining the action as a cost function, we actually found a neat connection with the kinematic space, which gives us the same functional for the circuit as one obtains from the action up to some absolute value that we actually understand. So that's all that I had to say, and I will be very happy if you have questions regarding my talk. Thanks.
Okay, so thank you very much, Michal, for the nice talk. So we can unmute our microphone and clap up to show our appreciation to Michal. Right, so now this is the formal time for questions. So if you have any question, please unmute your microphone and go ahead.
I have a question.
Of course, thank you.
Yeah.
Please go ahead.
In the total action that you have computed, you have neglected the bulk counter term, right? So I would expect that if you include the bulk counter term, then you should not get the potential term of the Liouville actions because it's divergent, right?
Exactly. Yeah, that's true.
So,
yeah.
So what is the specific reasons for neglecting these counter term actions? I mean,
Good. So thanks for the question. It's a good question. So the reason why we did it is that we wanted to reduce to the particle optimization as a special case.
yes.
And if you include the counter term, then you lose this connection because then what you're supposed to optimize is a thing that is only given by the kinetic term, and the optimum of this is omega equals to constant.
Right.
Like a trivial, flat boundary metric. So like that was the primary reason, but we also allowed to include the counter term in our analysis in the paper. We did not really pursue very much like this picture of with cost functions, but we allowed for the counter term to try to see how it modifies the connection with TT bar, and we just concluded that well, I mean it's going to be a slightly different variant of the TT bar deformation that is induced if you do include the volume counter term. So I mean in this sense we were quite comprehensive.
Okay. That's another question is that suppose you choose your surface z equals to rho t is just a asymptotic boundary. Okay, then
Yes.
do you also need this joint term?
I would say so, right? Because this joint terms comes from the fact that there is something connecting that. I mean, there are two surfaces connecting, right? So,
yeah.
So there's always going to be this stuff and this stuff connecting, right? So even if this is completely flat and resides at the asymptotic boundary, you would still need this term.
Okay. Okay. Thank you.
Sure. Pleasure. Thanks for the good question. For good questions.
Any other questions? Okay, it seems that there are no more questions. So, all right. So thank you, Michal, once more for the very nice talk, and it was a great pleasure to see you again after so many years. So thank you very much for the very nice talk, and thanks everyone for joining. And I wish everyone to have a very nice time. So thank you very much once more, and bye bye for now.
Yeah, thank you, Joel. Thank you for the invitation. Thank you for being for the talk.
Okay, sure. Bye bye.
Bye bye.